everyone. Today we'll be exploring a very interesting problem in graph theory called greedy merchants. So you can access this problem in codeforces. Uh, First, I'll be taking you through the problem statement and then about the input properties and then the examples. I will explain you the example in order to let you fully understand the problem statement. After that, we will go through all the missing pieces that we have to bring together in order to solve this problem. Coming to the problem statement, the Roman Empire consisted of n cities, and and there are m directional roads from 1 to m. So it's like a city with n roads and m bidirectional edges. So you can assume that you can model this problem as a undirected graph G with n nodes and m edges. And there are also other properties like any two cities were not connected by more than one road, so there are no multi edges. And also there are other properties like there existed a path between any two cities in the Roman Empire. So you take any node AI and any node BI, there always exists a path PI between AI and BI, implying that the graph G is strongly connected. There are K merchants, and each one is associated with a pair Si, Li, and one is the warehouse location, the other one is the shop location, and there's a property that says that a road which is equivalent to an edge is important if destruction of it would break the paths or makes it impossible to travel from Si to Li. Meaning, let's say this is Si, and then, sorry, this is another intermediate node 1, this is another intermediate node 2, and this is Li, and you can reach through from Si to Li via this path through n1 n2, or if you have another node like n3 which is connected to Si as well as Li, then you can also reach it like this. So if you look here, this graph is strongly connected. You take any two nodes, you will always find a path from that node to the other node. Which sounds like, which means, let's say here is Li, here is Li, and there could be multiple paths from Si to Li. So if you see this, so assume these are like wherever you observe the curves, that is where the nodes are there. Like there is a node here, there is a node here, and then there is a node here, there is a node here. So if you look at it, these are all the possible paths from Si to Li. What is an important road for this merchant I? It is this one, the one I'm circling here. Because if you remove it, yeah, if you remove it, then you can see that there is no way to grow from Si to Li because the graph became disconnected. So, which tells us that an important road is equivalent to a cut edge of the graph. And yeah, and what is our target? The output is 2 for every merchant I. we have to print number of important rows for that merchant. Yeah, so if we look at the example, you can see it on the right. The graph looks like this. You can say that this graph G with 7 nodes and 8 edges is strongly connected. Why do I say that it's strongly connected? Because you pick any two nodes, yeah, it's not actually strongly connected, it's just connected. If you pick any two nodes, then there always exists a path between those two nodes, as you can see in this graph. But what do we want to try here? So the thing is, let's take an example. So these are the locations of the merchants. Let's take the first merchant's locations, which is 1, comma 5. So these two are the nodes we are looking at. If you see, in order to reach from 1 to 5, you can go through via 1, 2, 3, 5, or you can go through via 1, 2, 3, 4, 5, or you can go through via 1, 2, 3, 4, 7, 5. So there exists numerous ways to reach from 1 to 5. In all these paths, we have to find edges so that when they are cut, all these paths will be broken, meaning the graph becomes disconnected. For example, take this edge between 1 and 2. If you remove this, if you remove this, then you can see that the connected graph got separated into two different components. So obviously, all your paths will break. Even this is invalid now, this is invalid now, this is invalid now. So between 1 and 2, there is one cut edge, and between 2 and 3, there is another cut edge, which will divide the graph into two components. It need not be just two, it can divide it into multiple components usually. But because this graph is connected, we can think of it like one cutting one edge would actually separate it into two distinct components. Now, so if you cut the edge between 3 and 4 or 4 and 5 or any other edge, then the paths between 1 and 5 won't get disturbed. For example, if you cut this edge, then still you have path 1, 2, 3, and 5, which is this one. You can cut this, but this is not affecting the paths from 1 to 5. So this will act as a cut edge when 6 is part of the merchant's locations. So yeah. So for every merchant, we have to calculate number of cut edges he has in those paths. That is our goal. And the prerequisites for solving this problem would be, so in order to solve this problem, there are prerequisites which you can read from internet, or I will also explain in this channel through some other videos. Is Sargent's algorithm to find cut vertices of the graph in a graph, and then binary lifting. I'll explain you what it is very clearly and how to arrive at such solution. So let's look at the problem. There is an undirected graph with n nodes and edges, and we're supposed to find for every merchant I, we're supposed to output number of cut edges in his paths. So these are the different pieces of the problem. So what we do is now we break the problem into different pieces and then we solve it one after the other. The important thing about solving such bigger problems is to break down problem into different subproblems where the algorithm for each subproblem is something we already know. So, so don't worry about the problem. Assume I have a black box that takes the undirected graph and it outputs all the cut edges present in the graph. So this black box is actually our Tarjan's algorithm. Let's call this black box as TB, Tarjan's black box. Assume you know all the cut edges of the graph represented by CEI as a set of cut edges. Now think of a naive solution or a brute force solution to this problem. Like if you already know what are the cut edges of the graph, then how do you find out what is the how many deniers or how many if you know all the cut edges of the graph, how do you find out for each merchant number of important roads for him? So it's like for every merchant, find out all possible paths that will take him from SI to LI. Let our output be the set of answer A. And what are the properties of A? A for merchant I will be subset of the cut edges as well as AI will be part of one of PIs. Why is that so? Obviously, for a road to be important, removing that road would actually disconnect the graph. And that is what the first condition is about. And disconnecting graph is not exactly sufficient because your SI will LI could be in the same component after the edge is cut. Let's say this is component 2, this is component 1. After this edge is cut, still SI and LI are in the same component. So you're not breaking anything between SI and LI. So this condition is alone not sufficient to say whether AI is actually an important road for merchant I. What is the other condition? AI should also be part of one of the paths that takes from SI to LI, if which means that LI should be in the other component. Only in that case you can actually make conclude that this road is an important road. Okay, so once we get the CEIs from the Trojan's algorithm, for each merchant we have to find number of such AIs. So what is the problem with the above approach? Finding the set of all possible paths per each merchant is almost exponential. So we have to find another way to get the cost per each merchant. To understand that, we have to change our perspective of viewing this graph. Assume that this is one connected graph. This is one connected graph. So it has 11 nodes and 13 edges. Okay, so this is a connected and undirected graph. And what I want to say is, let's find out all the cut edges in this graph. Let's see what we'll get out of it. So this is one, this is another one, and then nothing else. So there are three cut edges which are 2 comma 4 and 6 comma 7 and 7 comma 8. So how many components do these cut the graph into? So this is one component, this is another component, this is another component, this is another component. So total 4 components. Okay, so to which nodes is 2 comma 4 could be an important route? Only if the source is in one of the components and destination in any of the other components except the source component. Only then 2 comma 4 would be a important route as per the definition in the problem. So it is an important route for many pairs. So how do we get the solution out of this? The first step is that we use the Targets algorithm to get all the cut edges, the set of cut edges. And what do we make of these cut edges? So it's like if you see carefully for three disconnected components, sorry, for three cut edges, I got four components. So if I have n cut edges, the graph will be split into n plus 1 disconnected components. You can try it on any undirected graph, you will see the same result. And why is that so? Because each cut edge will divide one component from rest of the graph. And the first cut edge will split the graph into two components. The second cut edge will add one more component to it. So total it will be n plus 1 disconnected components. So it's like if you model each disconnected component as a node of another graph, and each cut edge is an edge in the new graph. For example, you see this is component, let's say C1, this is C2, this is C3, this is C4. So we have C1, C2, C3, C4, and if you draw the cut edges as edges of this new graph, you can see that you will not have any cycles in the graph. Because as we can see that for n plus 1 disconnected components, there are n cut edges. So for n nodes, there are n minus 1 edges. And also this resultant graph G dash is also connected. So if you can recollect, a graph that is connected and has these properties is actually a tree. Is actually a tree. So you take original graph, find the cut edges, disconnect them, disconnect the graph by cutting those edges. Now form each disconnected component as a separate node, and then form the edges between the new nodes where we remove the cut edges. The resultant graph is a Z prime, and it is also is a tree because it is well connected. Because the original graph G is connected, if you remove the cut edges and form them again, the resultant graph G dash will also be connected because you haven't removed any important cut edge. Because that is, you haven't missed any edges. And also there won't be any cycles in the graph. One property is that it is connected, and the other property is that G dash won't have any cycles. How do we prove it? It's simply because assume that G dash has cycles. So between component 1 and component 2, there are some intermediate nodes. There are several paths. If this is the case, then this edge, it can't even be a cut edge in the original graph. Because all the edges of G dash are actually the cut edges of G, you will not have two different paths from one vertex to another vertex. So it is acyclic as well as connected. So we can assume that the resultant graph is a tree. Now the question is, what do we do with this tree? Yeah, so assume that always the node with the first node assumption, the component with the node numbered 1, let's call it as C1 in all the graphs, in all the resultant graphs. Assume C1 is always the root of the tree. So it's like C1, C2, C3, or you can have C4 below C3, or in the above example, it's below C3, but you can also have like this. It can be like anything. It's just that the C1 has the node name 1. Assume that for now, to understand it in an easy way. Now, given merchant I, We have pair SI. Find out to which component does this vertex belongs to. Let's call it CSI, and the component to which Li belongs to is CLI. If CSI equals to CLI, then he will have to pay 0, because both are in the same component. There is no way you can choose a vertex, you can choose an edge which can actually disconnect both vertices. So the CSI and CLI will be one of the C1, C2, C3 or C4. So what if they're not equal? What if they're not equal? So what is the solution when they're not equal? Let's say we got that the CSI is C2, that the SI is in C2 component and LI is in C4 component. Just look into this tree. What do you think would be the number of important roads for this person? If you break this cottage, will it break any path from C2 to C4? No. And also, because there are no cycles in this resultant graph G dash, there will only be one path from CSI to CLI, or from any node to any node, because it's a tree. So in that path, if you break any edge, then that will break the tree. So all we have to do is find the height of this C2 from C1, H1, find the height of the C4 from C1, H2, just do H1 plus H2. So the solution would be H1 plus H2. But if the graph is like this, or the tree is like this, and let's say your SI is in C4, your LI is in C5 in the fifth component. Now, what is the solution for this? Here, if you breaks what the edge between C1 and C2, it won't affect in the path that exists between C4 and C5. This one. So, how do you find out what is the path or number of edges that you have to pass in order to reach C5? You find the least common ancestor for C4 and C5, which is C2. With respect to C2, find the height of C4 plus height or depth of C5. In this case, it is 2 plus 1. So these three are the important roads for merchant I. And yeah, so what are the steps? First is to find out cut edges using Tarjan's algorithm. Second step is to form a new graph from the existing graph by forming the components which are disconnected plus joining them using cut edges. What is the third step? Whatever is found, the G prime, which is a tree. Let me write the third step down. What is the third step? For all merchants MI, we have SI and LI. From the graph that is formed in the second step G prime, you give SI, LI, and you can actually, in the step 2, while forming the graph, you can use an unordered set or some other data structure to map each vertex in graph G to its component in graph G prime. I will dry run it on the example in order to help you understand. So it will be clear when I dry run the example. So let's call it CSI and CLI. For SI and LI, find their components and then find the LCA between CSI and CLI in G prime. Let's say that LCI is CLCA. Now you have to find the depth from CLCA to CSI and add both. We will get the answer for the ith function. Just print this. Now, what is the time complexity of this? Firstly, Tarjan's algorithm would take of V plus E because it's one DFS traversal. And the next step, that is to form G prime, would also take O of V plus E. And let's say there are K merchants. For each merchant, you're traversing the tree again. In the worst case, is again O of V plus E. So our overall time complexity would be, which is not very if this k is more, then this would be drastically more because it's multiplication. Iterate once, store some relevant info, which we call pre-processing, and then use it to answer each query. That is, to answer cost per merchant without iterating the graph again and again for every merchant. How do we do it? Yeah. So what do we want to optimize here? Let's say we already, for heights or depths, we can already traverse the tree once and assume C1 is always the root. You can always find out depth of each node in one traversal. So finding the depth is not a problem. It's about finding the least common ancestor. Usually, given a tree, the worst case time complexity can be number of nodes in the tree. So can we bring it down somehow? Can we make it better than O of n? Well, I think we can. We can bring it to O of log n. And for a graph with n nodes, in the worst case, there could be n disconnected components. So the resultant graph will also have n nodes because our final step is actually on the resultant graph. For k queries, that is the k merchants, each step in, like I said, if you go via a brute force way of finding LCA, it would take O of n, but it can be reduced to log n if you do n log n for pre-processing. So yeah, if you spend n log n time complexity on pre-processing, you can decrease the query time from O of n to O of log n for each query. So the time complexity would be n plus number of edges of the original graph. This is for Tajan's algorithm, and then n log n pre-processing. And the formation of new G dash would also take the same amount of time complexity, so I'm not mentioning it. And k log n to answer each query. How we will get it from O of n to O of log n is actually very interesting, and it's so let's explore a technique called binary lifting. Try to give you the intuition behind it because it's a very common technique in the competitive programming to actually find the lowest common ancestor whenever there involves multiple queries, and you can get it from log n per query. So what does this LCA take? It takes two nodes A and B that are part of the tree, and it will give you the lowest common ancestor in the tree. Let's say that that node is called LCA such that it will divide the tree in such a way that A and B will be in different subtrees. You can find out about what LCA is in the internet. In this video, I'll only explain about the binary lifting and the intuition behind it. So in order to explain the binary lifting, let's take one big tree because the binary lifting actually works in the powers of 2. So 2, 3, 4, 6. Let's just say, and also there are some other nodes. Yeah. And let's say this is the component where the SI is, and this is the component where the Li is in the final G dash G prime tree. Now, usually, what is the intuition of binary search? It's like you have some objects to jump, and instead of jumping one to the other, you jump somewhere in the middle or somewhere far and find out whether this object is satisfying this condition or not. And because of the nature of the elements and the way they are ordered, you can figure out whether to go to left or to go to the right. That is the nature, that is the intuition behind binary search. Now, is it possible to somehow find the LCA of these two nodes here without actually jumping all the way to the common ancestor? Like, what is the naive way? First step is to bring CSI and CLI to the same heights or depths from root. And the second step is start moving up until both sees the same node. But like I said, this can take O of n in the worst case. So what is the other way? What is the other way? Whatever the algorithm we go with, we first have to bring them to the same height. So we take the CLI till here first. We ensure that they are at the same height, both CSI and CLI. So both are now at the same height from the root, which is this is like 6 edges from here, and then total you have to travel 11 edges from root to go to either of CSI or CLI. So after you bring both nodes to CLI, let's see what we can do within the tree. Now, if I tell you that for every node, I have an array or a map, something, where the key is number of times you want to go up. It's like CSI of 1 will be the parent of CSI, and CSI of 2 will be parent of CSI, which is like the grandparent, that is this node here. So let's say I have this array, which I found as part of tree processing. But the problem is to found this kind of array for every node, you're like traversing up the tree. So it's O of n square in the worst case. We're not making it any better. So we have to reduce the way we are storing the pre-processed data. So instead of storing all the parents' data per node, let's just say I only store, let's say my array is up for node I, it is up. Let's say the element I will represent the 2 power ith parent of up. Why? How am I coming to this conclusion that it should be 2 power I? Because obviously you can't store all the elements. Would storing this help us in some way? I will give you intuition for why it can help us. Now, your LCA will be at some height related to CSI. Yeah, for now, assume that we already brought CLI to the height of CSI. So yeah, so if it is at some height relative to CSI, meaning this relative height would be number of edges between the least common ancestor and CSI. Let's call this as our DLCA CSI, which is, let's say, L simply. L has some binary representation, and as per the test cases, L won't have more than 20 bits, or assume, let's say it's 32 bits to make it simpler. In the binary representation of L, there will be 32 bits. Each bit B31, B30, so on, B0 can be 0 or 1, but I don't know what L is. I only know that L can be represented in a binary format. So what do I do with this binary format exactly? Let me give you that intuition. So L be the relative distance between the least common ancestor and CSI. L has some binary representation. But what do we do with this binary representation exactly? We don't know what each bit is, but is it possible to find out? Yes. When is it possible to find out? Let's say assume that the 31st bit is 1. Okay. If you assume that the 31st bit is 1, then obviously the relative distance would be at least 2 power 31, because the rest of the entries can be zeros or ones, but at least the value at this position is 2 power 31. So the distance can be 2 power 31. If I can find out what is the 2 power 31st parent of CSI, if I know this, and also if I know the 2 power 31st parent of CSI, if both turned out to be equal, now what is my criteria to actually evaluate whether Li will have its 31st bit as 1? So how would our LCI look like? So this both nodes, what we want is that they should not be ending up at the same node. If they're ending up at the same node, then it means the 2 power 31st node will be somewhere around here. I mean, not in this example, but it will either be LCA or it will be one of its parents. Yeah, only then, because you cross the subtrees and you are eventually going into the common tree. So, but we don't want that condition to be satisfied. We want to end up in one of these nodes, no matter where the our CSN and CLIs are. Or simply put, in this example, we want to end up at these nodes so that the final condition would be such that immediate parent of both nodes that we will eventually end up will be same, which is this. We want to go to a node that satisfies this condition, because if you go to a node that where both are equal, both CSI of 2 power 31 and CLI of 2 power 31, you don't know whether you ended up at CL, LCA or in any of the above nodes. So that is the case. So yeah, it's 2 power 31, and if you end up at a node, simply put, if let's say node of I represents ith parent of the node. So the condition we want is CSI or 2 or I shouldn't be equal. If they're not equal, then we still have chance to jump up. If they are equal, let's say you took like 4 hops, you went till here. Here you have chance to jump extra, but if you directly took it from here till here, then you don't have any chance to go up or towards the LCA. So yeah, this is the condition we'll be following. So from 31st to 0, find out up for CSI of 2 power 31, up of CLI for 2 power 31. If they are equal, then assume that you can assume that the 31st bit should be 0. And we move to 30th bit. It's the same process. Eventually, the intuition is that, if you take this example, you have to move like 1, 2, 3, 4, 5, 6 steps in order to reach the LC, least common ancestor. But we don't know that there are 6. Assume that it's a 8-bit system. Just assume that for a simple, because it's a very simple example, just assume that it's 8-bit. Now look at the first one. Start it from MSB, go till LSB. So you start from MSB, assume, let's say this is our answer height at which the LCI is present respect to CSI. We want to find out whether the 8th bit is 1 or 0. Assume it's 1. Then obviously your height will be at least 2 power, like this is 2 power 0. It's like 2 power 7. But there are actually very less jumps you can do here, 6, 7, 8, 9, 10, 11. So this will take you beyond the root. So you don't want it to be 1, you want it to be 0. Similarly, for 2 power 6 till 2 power, this is 0, this is 0, this is 0, this is 2 power 4. What about this 2 cube? What if you take 8 jumps? Then you reach here from CSI, even from CLI, you reach the same node. Let's call this node as C4. So if you take 8 jumps from CSI, you reach C4. If you take 8 jumps from CLI, you reach C4. This is not something we want. We don't want the equality.
So assume it is 0. And then what about 2 square? Take 4 gems from CSI. 1, 2, 3, 4. Let's call this C8. So CSI, when it took 4 gems, ended up at C8. And let's say, and CLI, when it ended up at something which is of same depth at where C8 is present. Let's call it C8 prime. And C8 is not equals to C8 prime. So you can assume it's 1 here and move both CSI and CLI to these positions. So here is the new CSI, here is the new CLI, and then 2 power 1. What if you take 2 steps? You will end up at, let's call it C5. If you take 2 steps, CSI is currently here. If you take two steps, CSI will end up at C5, CLI will also end up at C5, and both are equal, which is not what we want. So keep it as 0, and then take 1 step. The only one left is 1. So from C8, if you take this, you will go to C7. From C8 prime, if you take 1 step, you go to C7 prime, and C7 is not equals to C7 prime, so you can take that step. What is this value exactly? It's 1, 2, 4, which is actually 5. So whatever the resultant you have is h minus 1. So only by going through 8 iterations, you found out what h minus 1 is. This h is actually LCA minus CSI, which is 6 in this case, and you got 5, which is one step below the LCA. We only want to reach nodes which are one step below the LCS through this binary iteration. So that is the thing. And if you observe, what we have to know, each element in the binary representation is of value 2 power I. All we have to know is, whether 2 power ith parent of any node. If we know this value faster, then we can say whether we ended up at the right nodes or not. So as part of pre-processing, we calculate this for every node. So it's like, if the height of the tree is n in the worst case, it's log n iterations per node, which is n log n, to just build those height, that is up arrays per node. So that is the intuition. It all boils down to approximating the binary representation at which the LCA could be present. So first we went through Tarjan's algorithm, and then we went through binary lifting. You need this to find cuttages. You need this to find LCA faster. So once you know where the LCA is, it's easier to find out depth of CSI relative to LCA and depth of CLI relative to LCA. You can see it in the code I will be showing. So this is the intuition behind binary lifting. Now let's dry run a case which is given in the problem. Original graph. And the first step is to find the cut edges, which are 1 comma 2, 2 comma 3, 5 comma 6. I'm not running the Tarjan's algorithm because it is very generic and you can learn about it through available online resources. So these are the cut edges, and then I remove them, and then I draw a different graph. So there used to be a cut edge between 1 and 2. So I'm joining those disconnected components now between 2 and 3 and between 5, 6. Let's call it C1, C2, C3, C4. This is the resultant graph G prime. Yeah, for C4, let's define an array UP of I such that UP of I represent to power ith parent R. So for C4, UP of, so yeah, let me draw it here. For C4, this is like the first element will be first parent. This is 2 power 1, which is second parent. This is fourth parent. This is eighth parent. Because we only have 4 nodes, we can about this. So for C4, its first parent is C3 and then C2, and this is you can assume minus 1. For C3, it's C2, C1, because there is no fourth parent for neither C3 nor C4. For C2, it's C1 minus 1 minus 1. For C1, it's minus 1 minus 1 minus 1. Because C1 is the root, so your tree would look like C1, C2, C3. This is what we are doing as part of pre-processing. Now, let's go through the third step, which is addressing the queries. If you look at the test cases, the locations of the merchants are like 1, 5, 2, 6, 4, 7. These are our SI and LI. Let me So let's see what are the corresponding components of them in Z prime. The first node is in C1 and the fifth node is in C3. The second node is in C2 and the fourth node is in C3. The second node is in C2 and the sixth node is in C4. The fourth node is in C3 and the seventh node is in C3. Now take C1 and C3. Obviously, C1 is the lowest common ancestor for C1 and C3, and there are two paths, sorry, two edges between this path between C1 and C3. So the answer would be 2. If you want that, if you want to dry run the binary lifting, then for the first step of binary lifting is to bring both C1 and C3 to the same height. When you do that itself, you will get the height 2. So first one would be 2, and between C2 and C3 is the same case. Between C2 and C4, because this tree is very linear. Before you apply the LCA itself, you will be bringing both nodes to the same level and both nodes will be matching, so you won't apply the LCA and simply take the steps of how many you incremented to bring the other node to the same level. And between C3 and C3, it's 0. So and if you see the output, it's 2120. Okay, now let's go through the code. Initially, you take the inputs to actually form the graph, and then you form the graph, and then this find cut edges method is what the Targent's algorithm is all about. You use DFS to find out all the cut edges. So after you form the graph, the next step is to find the cut edges, and the next step is to actually count the bridges per merchant, like number of cut edges that are present for each merchant's paths. And how do we do it? For that, we have to form a new kind of tree, like I said, Z prime. Like you can see in step 4, the above step is about getting the component numbers in the disconnected graph for each vertex, and here you form the tree. After that, like I said, we do some kind of pre-processing. The first is to actually find the depth, and the next is to actually form the up array, that is to help with binary lifting, and the next step is to iterate through each merchant locations, and if they are in the same component, then you have 0 cut edges. If they're in different components, we find the LCA, and the number of bridges would be depth at which the CS or whatever the first component is present, and the depth at which the LCA is present, plus the depth at which the second element, like it could be the shop's location minus depth of LCA would give us the number of edges in the tree's path from CW to CS, and just return it the result and print it out.